In the previous class, we had started the topic of vibrations of geared systems. And we had learned that whenever inertia elements are connected through shafts and then through gear trains, then we have a mechanism of devising, or rather converting this system into an equivalent system in which either the inertia of the gears is ignored or it is considered. And based on both of them, there will be an equivalent conversion of the geared system into a system that we are more familiar with. For example, initially we studied that if we have a geared system like this, it is connecting two shafts and each of the shafts is carrying its own inertia element. So this particular figure could actually be representing any sort of driving mechanism. The first inertia element could be the engine, and the second inertia element could be the thing that is being driven. For example, I1 could be an electric motor and I2 could be a pump. So there are a lot of day-to-day things or engineering artifacts that can actually be represented by this simple line diagram showing two connected gears. So in the first place, if you ignore the inertia of gears, you would be aiming at converting your system into a system like this. Okay. So basically what you are trying to do, or what you're trying to achieve, is you are basically converting the driven side of your system. See, this entire assembly is the driver side, and this entire assembly is the driven side. So basically what you're going to do is select the entire driven side and convert it into an equivalent mechanism like this. That means you are going to put an equivalent inertia element here and an equivalent shaft here. In the driving side, the inertia element, that is the disc and the shaft, they are the same as of the equivalent system. Okay. So we had done the derivation, we had looked at the mathematical aspect of how to convert this into this equivalent system. And in order to do that, if we skip the derivation part, which we have already covered in the previous syllabus, the only thing that you have to do is to make a replacement like this. So this is the original system. What you are being shown here is the original system. And this is the equivalent system. Now, as you can see, in the original system, there are two gears, and in the equivalent system, we have conveniently eliminated the gears. And as a compensation, what you have to do is you have to convert the shaft that was on the driven side into an equivalent shaft with the shaft spring constant, that is the torsional stiffness being equal to n square times kt2. See, kt2 was the original stiffness of the shaft, and n square kt2 is the stiffness of the new equivalent shaft that you are going to replace the original with. And what is this n? This n is called as the speed ratio, and this is nothing but the ratio of RPMs of the driven side to that of the driving side. So if N2 is the RPM of the second rotor and N1 is the RPM of the first rotor, then speed ratio is simply given by N2 by N1. So this is a dimensionless quantity. It's just a number, a real number. So all you have to do to eliminate this gearing and replace the equivalent shaft is to make the stiffness of the new equivalent shaft equal to N square KT2. And similarly, on the driven side, there is a rotor of inertia I2. Now that also has to be replaced by a new rotor having a new inertia of N square times I2. So as you can see, the only thing that you need to remember to make the replacements, all you have to do is select all the elements of the driven side, multiply each parameter with the square of the speed ratio, and you get the quantity or the new parameter with which the replacement has to be made. So once again, to be precise, KT2 shaft is replaced by an equivalent shaft having stiffness N square KT2. I2 rotor having inertia of I2 is replaced by an equivalent rotor having inertia of N square times I2. So only this factor of N square has to be remembered. So all you have to do is multiply all the driven side parameters with N square, where N is the speed ratio. So you get the equivalent replacement entities. And now, once the equivalent replacement entities have been put in place, you can conveniently ignore the gearing mechanism. So this was the concept of the first technique that we are using, the first technique in which we want to eliminate, or rather we are saying that we are ignoring the inertia of the gears. Now if the inertia of gears is considered, see, all this analysis that we have learned till now was analysis number one, where the assumption is that you are ignoring the inertia of gears. Now the second one, what happens if we consider the inertia of gears? Now you are not allowed to eliminate these gears altogether. So what you have to do is, definitely on the driven side, your shaft has to be replaced with an equivalent shaft. On the driven side, your rotor has to be replaced with an equivalent rotor. But the gearing also has to be replaced with something equivalent, because now you're considering the inertia of the gears also. So what should we do? Now we have already studied how the inertia of a driven side element is converted into an equivalent element. So we do not need a detailed derivation anymore. We can simply say, how many gears did we have? We had two gears. One gear was on the driving side and one gear was on the driven side. What happens when you replace any entity on the driven side? Whenever we replace any entity on the driven side, all that we have to do is multiply the entity with square of n. So what I'm doing is, if I want to replace this gear, but I want to remember that its inertia is not forgotten. So without forgetting the value of inertia, if I want to eliminate this gear and put a simple shafting mechanism like this, then all I have to do is I simply have to multiply the inertia of the gear, which let us call as IG2. 2 represents, the suffix 2 represents anything that is on the driven side. The suffix G represents gear and I represents inertia. So IG2 means inertia of the gear on the driven side. So if I want to replace it with an equivalent inertia figure, or with an equivalent replacement figure, what I have to do is I have to multiply IG2 with n square. So now the original gear is gone and I have an inertia element. Now this is a hypothetical inertia element. This need not be in the shape of a gear. It should be some sort of a rotor having an inertia of n square ig2. That's all. So I have a rotor of n square ig2 in place of the gear that was in the driven side. Now what happens to the gear that is on the driving side? On the driving side, we do not make any conversions. Everything on the driving side is maintained as it is. So the original inertia of the gear on the driving side was IG1. That means one suffix indicates anything that is on the driving side. G is for gear, I is for inertia. So IG1 means inertia of the gear on the driving side. Okay, so we are not going to replace it with anything. We will simply take the inertia as it is. So now the question is, I want to eliminate both the gears from the picture, but I want to retain their inertia values. Now, when you say that you are retaining inertia values, that means some rotor shaped thing has to be placed where the combination of gears was placed. Now, you please pay attention to this part of the figure in the original setup. In the original setup, you can see in this part you are having two gears. Now, instead of these two gears in combination, you are simply putting a bulk rotor here. And then you can have the shaft continuing towards the right side and the shaft continuing towards the left side. So the left side part to this central rotor becomes the driving side. The right side to this rotor becomes the driven side. So you have equivalent for this figure, for this, and for this. These all will be having equivalent things, and this part will be retained as it is. And now if you go back to the equivalent converted system, I1 as it is, KT1 as it is, instead of the combination of both gears, you put a new rotor in place which has the combined inertia of both the gears. Now, out of the two gears, the first gear is on the driving side, so inertia of the driving gear will be maintained as it is. And the second gear is on the driven side. So you multiply the value of inertia of the driven side gear with n square. And now since this rotor block represents the combination of both the gears, you can simply say that the inertia of this equivalent rotor that I'm putting in place here would be nothing but the sum of the inertia of the two gears, the replacement equivalent and the original from the driving side. That's it. So it's simply IG1 plus n square IG2. And now the only elements that remain or that need conversion are that on the driven side. And you already know what has to be done to the elements that are found on the driven side. You have to multiply each parameter. For example, you want to find out what is the stiffness of the shaft. Okay, you have to make a correction here. This is not square here. The square will not come. It is simply KT2. So to replace the shaft on the second on or the driven side with an equivalent shaft, you have to multiply it with n square. So n square KT2 gives you the value of stiffness of the shaft or the equivalent shaft on the driven side. And similarly, the rotor on the driven side was having an inertia of I2. Now you replace it with a new rotor having an inertia value of n square I2. So this is the equivalent replacement. And after making all these replacements, you get a system like this. So this is how you convert a system when you consider the inertia of the gears. So once again, I will summarize both the cases. This is case number 1. Same figure. This is the original figure. And this will be the equivalent figure if you ignore the inertia of gears, and the equivalent figure will change if you consider the inertia of gears. See, on the driving side, IG1 remains the same, KT1 remains the same, and instead of both these gears, you are placing a new equivalent rotor. This will have the inertia of, okay, this is not IG1, this is simply I1. IG1 will be written as it is plus n square times of IG2. This is the total replacement equivalent rotor. On the secondary side or the driven side, the new stiffness will be n square KT2. The new inertia will be n square I2. This is how you make the replacement. So just have a look. Equivalent system to be constructed from the same original system. When inertia of gears is ignored, you get a 2 degree of freedom system. When inertia of gears is considered, you get a 3 degree of freedom system. Now you see there are three inertia elements: first inertia element, second inertia element, third inertia element. This is how you convert the system. So there are two options. Now, depending on the problem that is being asked, all that you have to do is first identify whether the inertia of the gears has to be eliminated or retained. If it has to be eliminated or ignored, if it is said in the question that ignore the inertia of gears, then you go for this conversion. And if they ask you to retain the inertia of the gears, you go for this conversion. This is how you do it. And once you have obtained the conversion in the required manner, then you can proceed with the problem of finding the natural frequencies. See, we should not lose vision of the original thing that we were actually after. We wanted to find the natural frequencies of the system when there are gears involved. So we don't know how to deal with the change of velocities and all that stuff when gears are involved. So that is why we go for equivalent conversions, because if such a system is given to you without mentioning that it was obtained from a geared system and all, and simply if somebody asks you find the natural frequencies of this system, no equivalent or anything, just this system is given to you out of the blue, how would you do that? Let us see. See, now the thing is, somebody gave you a problem that there is a rotor of inertia I1. It is connected with a shaft of stiffness KT1, then another shaft of stiffness KT2 in series, and then another rotor of inertia I2. What are the two natural frequencies? This is a 2 degree of freedom system. How would you calculate it? The first step in treating this problem is to replace this stepped shafting with an equivalent shaft having a uniform diameter and a singular value of shaft stiffness. How do you do that? You just have to treat it like a case of two springs in series. See, the shafts are nothing but springs in torsion, right? So if you ever feel confused in rotary systems, you just go to your rough page and draw an equivalent system like this. See, instead of the shafts, I'm simply drawing two springs, and instead of KT1, I write a spring constant K1. Instead of KT2, I write a spring constant K2. Now, how do you convert these two springs in series into an equivalent spring? It's very simple. The formula for conversion is 1 upon K equivalent would be equal to 1 upon K1 plus 1 upon K2. Now, just for the record, so that you remember in other cases, if the springs had been in parallel, then the formula for K equivalent would have been simply K1 plus K2. Many students confuse these formulae. For parallel, they apply this formula. For series, they apply this formula. So you should keep it in mind. It is for parallel springs that the conversion equation is K1 plus K2. For series, you have an equation like this, right? So all that we need to do for this one is, now since for straight springs you know the equation like this, so it's exactly applicable in the same manner for torsional stiffness too. So KT1 and KT2 are torsional stiffnesses. They are obtained in rotation, but don't worry, the formulae for conversion into an equivalent shaft would be exactly similar to this. So what do you do? What is the equivalent stiffness, which I choose to write as KT equivalent? This will be equal to 1 upon KT1 plus 1 upon KT2. Now, since KT1 and KT2 are known, you can easily calculate the value of KT equivalent. And once KT equivalent has been calculated, your system becomes like this. A simple standard problem of 2 degrees of freedom system. Now you know the value of I1, I2, KT equivalent. Obviously, this I2, this new I2, let us call it as I2 dash, this has an actual value of n square times I2. This is the only thing that you have to remember. That's it. And in this KT equivalent, this KT2, let us choose to call it as KT2 dash, because this is not the original shaft stiffness that we had. This is a converted equivalent value. This was actually, the value of this is actually n square times KT2. This being the only difference, now you know how to convert a geared system into a stepped shaft system. And once the stepped shaft system is obtained, you convert the stepped shaft into an equivalent shaft by using the series spring combination formula. And once you obtain it, you proceed with solving this problem exactly like you have solved any other 2 degree of freedom system problem. That's it. This is how you do it. Okay. Now, just for practice, let us see a few problems that are likely to come in your RTO exam if they come. Okay. Now, this is a problem from GK Grover book, illustrative example 6.5.1. Now, the problem says the figure represents two single rotor systems connected by a non-slipping belt. Now, you see, instead of a gear, they have given pulleys and belts. So, you see, this is pulley number one. Pulley number one is connected through belt to pulley number two. So, the inertia is only on the pulleys. Okay. On the left side of the pulley, there is a shaft of stiffness KT1 dash. On the right hand side of pulley 1, there is a shaft of stiffness KT1 dash. So basically these two are the same shaft material continuing through the pulley. Okay. Now after the belting has been connected with the pulley of inertia J2, J1 and J2 are the inertias of the pulleys that are given. Okay. The left hand side and the right hand side are once again connected with shaft stiffnesses of KT2 dash and KT2 dash on both the sides. Now, what is the question here? Find the natural frequency of the system. Now, obviously, you don't have any practice of dealing with pulleys, belts, different shafts, shafts in parallel series. So all that you have to do is, first of all, find a way of simplifying the given system into a system that we are more convenient with. How do you do that? Now you see, let us first observe the first shaft and pulley system. The first shaft and pulley system is like this. there is a bearing here. It's not shown in the figure, but it has to be there. Otherwise, how would the shaft be held in air? So even if the line diagram is not showing something that is obvious or which has to be logically there, you just consider it like that. Okay. So on two bearings on both the ends, the shaft is connected and the stiffness is given as KT1, KT1 dash on both sides. J1 is the inertia of the pulley number one. Okay, so we are considering only the parameters on the driving side. So the top part is assumed to be the driving side, the bottom part is assumed to be the driven side. Obviously, it could be the other way around also, but let us consider it like that. Let us see if something is given in the problem. Two single rotor system convert the system. Okay, nothing is given which is driving or driven. So you can easily assume one to be the driven and one to be the driving side. It could be vice versa also. Anyway, for this system, if you are not convenient with rotary mechanisms, as I have already told you, the simpler way to deal with such systems is to take an equivalent linear system. So instead of the torsional stiffness KT1 dash, you will have K1 dash. Instead of inertia of the rotor J1, you will have mass M1. And instead of KT1 dash, again, you will have K1 dash and then a fixed end. The bearings do not allow for lateral or linear any sort of displacement of the shaft. So you can consider them basically as fixed ends when you are taking equivalent springs for them. Now, how do you convert this spring mass system into a more convenient format? Forget about the rotary systems. Okay. Now, as you can see, whenever you have two fixed ends, a mass in between, and then springs on either side of the mass, then you can simply say that the springs are not in series. Although this looks like a series setup, this is a very, very tricky situation. These springs, they appear to be in series, but you have to remember the springs will only be in series if they are actually connected with each other. Then they will be in series. If you put a mass in between the springs, then the springs actually become in parallel. So this is something that you have to remember. We have already deliberated on such issues, so I will not dwell on it, why this is in parallel. And I would rather encourage you to go and look it up yourself. Try to do a little bit research on the internet. And why? Try to find out why when springs are connected on either side of a mass, then they actually behave like springs in parallel and not springs in series. So anyway, treating them as springs in series, the equivalent conversion for this would be simply to add the springs up, because what is the equivalent spring constant of two springs in parallel? You simply add them up. So I will say that I put a single spring in front of the mass here, and the spring constant of this spring, new spring, becomes twice of K1 dash. So that's all that you have to do here also. Now we are not having a linear system. Actually, we are having a rotary system, and we draw a linear system to simplify things for us, because rotary systems, as a general matter of fact, are not convenient topics for most of the people. So that is why we take a more convenient route by selecting a linear system as an example. Now for rotary system, if I make the similar conversion, just imagine that the shafts on both ends are acting as springs. And again, they are obviously in parallel because they are connected on either side of a centrally located rotor. So I can say that this system, the one that I'm drawing right now, which has shaft on only one side, is equivalent to the above system if I take the stiffness of the shaft on the left hand side to be equal to twice of KT1 dash. Why? Because I have basically done nothing but converted a parallel torsional system into a single equivalent torsional system. The inertia of the mass will remain the same because I have not actually connected it to the other gearing at the other end. So I do not know which is primary, which is secondary, which is driving, which is driven. I simply know that I have converted a given system into a simpler system. And similarly, if you look at the driven side of the shafting mechanism, once again you have got shafts of same stiffness on either side of an inertia element J2. So we will convert this system also. The secondary system will also be converted. So this will be J2. And this will be twice of KT2 dash. Once again, we have managed to convert a parallel connection into a singular one-sided connection. Now, this is the driving side and this is the driven side. And if you see, this becomes a problem very similar to the one that we have developed all our equations for. See, you have basically converted into a mechanism like this. Now, only difference being, instead of two gears actually coming in close proximity to each other, we have pulleys separated by a belting mechanism. That's all. So instead of actual gears connecting them, you simply have pulleys connecting them. So it does not matter whether actually gears are connecting them or pulleys are connecting them. So the pulleys are connecting these. The pulleys are connected with the help of a belt. But anyway, the question states very clearly that there is absolutely no slip between the belt. So a belt and pulley system having absolutely no slip is basically exactly the same as two gears connected with each other, because the gears were developed in the first place to eliminate the disadvantage of slipping of belt over pulleys. गियर्स का जो पुली और बेल्ट सिस्टम पे मेन एडवांटेज है वो यही है कि वो फिसलता नहीं है, फिक्स कांटेक्ट है वो. तो अगर आप ये कह दो कि पुली और बेल्ट के बीच में आप ये मान लो बिल्कुल स्लिप नहीं हो रहा है, so basically what you're saying is they are as good as being connected to two gears. So all the conversion formulae remain exactly the same. Now you see this side KT1 dash and KT1 dash have been added. This side KT2 dash and KT2 dash have been added. And now what do we do in order to eliminate these pulleys? Now in the question there is no mention of the pulleys inertia being ignored. Now apply a little logic also. If you ignore the inertia of the pulleys, then there is no inertia in the whole system. The entire system becomes inertialess. Now that is not possible. So in such a situation, even if the question does not state very clearly whether you have to ignore the inertia or not, what would you do? क्या करोगे आप? लॉजिक लगा के देखो. अगर पुलीज की इनर्शिया आपके पास में पता है, आपको दो चीजें पढ़ाई है. There are two directions that you can take. One direction that you can take towards solving a problem is to ignore the inertia of connecting elements, and the other direction is to consider it. But in this problem, if you ignore the inertia, what happens is your entire system becomes inertialess. So the obvious course of action that you have to take without being told is that you have to consider the inertia of the pulleys here. तो अगर अपन पुलिस की inertia को consider करें तो क्या करेंगे? On the driving side, the inertia is J1. You retain it as it is. On the driven side, it is J2. So you convert it into an equivalent inertia element by multiplying it with n square. So n square J2 is the equivalent one. And now J1 plus n square J2 becomes the total replacement inertia element of the system. And now the separation between the shafts can be eliminated, and you can put a continuous shafting like this. Once again, shaft on the left hand side and shaft on the right hand side are there. But obviously on the left hand side, since we have a shafting of the driving system, we do not convert it. So what is this kt1? This kt1 is actually nothing but the sum of kt1 and kt1 dash and kt1 dash, which were on the both sides. इन दोनों sides पे जो आपने ये लिखा था, यही same चीज है आपकी kt1. Okay. On the driven side, you again have kt2 dash and kt2 dash. You add it to get kt2. So let us say that this is kt2 now. But again, since this kt2 is on the driven side, you have to take an equivalent conversion for that. So you convert this sum, or rather kt2, by multiplying it with n square, which is what we do to get the equivalent system on the driven side. यहाँ पर भी n square से multiply किया था driven side वाले को, यहाँ पर भी multiply करेंगे driven side से. So the final system looks like this. On the left hand side, you have the shaft stiffness of kt1. On the right side, you have the shaft torsional stiffness as n square kt2, and the equivalent rotor in between as j1 plus n square j2. Now, is this the final setup, or can we further simplify it? इसको और simplify किया जा सकता है. Now you can see that kt1 and n square kt2 are again in parallel. So you can go for a further reduction of the system. So let me draw it and then show you how the final system is going to look. The final system, according to me, should be something like this. I will convert it into a single shaft and rotor system instead of a two shaft and rotor system, and take the stiffness of the shaft equal to kt1 plus n square kt2. I am adding them because the shafts are in parallel, and the rotor remains as it is, j1 plus n square j2. So this is the final setup. Let me show you. This is the final setup. And now the whole question in which this image was shown to you and asked what is the natural frequency of this entire system, all that you have to do is find the natural frequency of this simplest of simple systems. Now this, after all the conversions that we know of, we have obtained a single shaft and rotor system. And instead of looking it from a horizontal perspective, if you just view it from a vertical perspective, you will see that this is nothing but a torsional pendulum. And torsional pendulum can be horizontally placed or it can be vertically placed. It does not matter, because you are not giving lateral displacement to this pendulum. You are simply going to rotate it or twist it and release it. So whether the torsional pendulum is acting in a horizontal direction or vertical direction, the nature should not be affected. So this rotary system once again can be simplified for your better visualization as a linear system comprising of simply a linear spring constant K and mass M. What would you say is the natural frequency of a simple spring mass system like this? Obviously, I am 100% sure that all of you would say the natural frequency is under root of K by M. Now, what if instead of a linear spring and mass, we have a shaft and a rotor like this, in which the stiffness or the torsional stiffness is kt and inertia is I, then the natural frequency would be under root of kt upon I. Now, using this formula, what would you say is the natural frequency of this system, which we have eventually reduced our original system into? We have the inertia, we have the stiffness. So all you have to do is simply state omega n is equal to under root of kt1 plus n square kt2 divided by, that is the stiffness divided by the inertia. Simply write down the values, that's all. J1 plus n square J2. This is your answer. Let us check. Okay, so we have arrived at the right answer. I hope you have understood how we solved this problem. Let us look at a new problem now. It says an electric motor rotating at 1500 revolutions per minute. Now electric motor is there, okay? Now they're actually giving you some real world problem. Instead of simply giving you line diagrams showing some rough gears and rotors and all, in which you do not know what is actually happening. So electric motor is the driving element. Motors are drivers. RPM of the driving part is given. It drives a centrifugal pump at 500 revolutions per minute through a single stage reduction gearing. Now, I don't have the figure here, but even if they do not give you a figure, you can simply go for the figure as has already been taught to you. So let us say that I have a pump, or sorry, a motor on the right hand side, so on the driving side. Motors are generally drawn like this. Then there is a gear. Obviously, gears are used for transmitting power from one shaft to another shaft. And if there is one gear, there will definitely be another gear on the driven side. And this is connected once again through a shafting mechanism to the impeller of a pump. Now, what do you do? The electric motor which is driving, it has coiling, magnets, bushing, and all those elements are there which have got inertia, which have got mass. So for simplification, what you do is you do not draw a motor here. You simply replace it with a simple line diagram of a rotor. And you say that this is the driving inertia element. Let us say this is I1. The gear is there. Let us say the inertia of the gear is IG1 of the driving gear, and the driven gear is IG2. And obviously the impeller of the pump that is rotating looks like it has got all the fan, the fins and all. But for your case, you will simply put an equivalent rotor. So you see, the initial figure that we used for derivations is nothing but something that represents the real world entities. So I1, I2, they were simply provided to you as some random disks, but you know that these disks now represent actual systems. So the disk number 1 having inertia I1 is basically your motor, and disk number 2 having inertia I2 is basically representing your pump impeller. And the motor is running the pump with the help of a single stage reduction gear comprising of the driving gear IG1 and driven gear IG2. So you see a real world system, but once again reduced to a problem of a simple line diagram. Now, once the line diagram is there, you will automatically remember all the formulae that are associated with it, right? And if I had given you a actual figure of pump gearing, then it would have literally blown your mind. You would say, ये कहाँ से problem दे दी, ये तो हमारे syllabus में ही नहीं है. Anyway, so this is the problem. The data is given. So driving side RPM is given, driven side RPM is given. So the first thing is to find the value of the speed ratio, that is N2 by N1. That would be 500 upon 1500. So this is the value of N that you can calculate. And then the inertias of the electric motor and the pump are given. So I1 and I2 are eventually given. The pump shaft and the motor shaft, their lengths are given, their respective diameters are given. Neglect inertia of gears, and capital G is given. What is capital G? Capital G is modulus of rigidity of the shaft material. And you should know what to do with this data. See, if you look at the problem, what is the data that you needed and what is the data that is given? Here you need KT1. Here you need KT2. These are the things that you require. But instead, what is given? Instead of KT1 for shaft number 1, they have given you the length, they have given you the diameter, and they have given you the modulus of rigidity. What do you do with this? You should always remember that the default formula for calculating the torsional stiffness of any shaft is Gj upon L. Now what is J? J is the polar moment of inertia of the cross section of the shaft. And since shafts are generally circular in cross section, you simply have to remember the formula for a circular area, the formula for polar moment of inertia of a circular area, which is pi d raised to power 4 by 32. So since the diameter of the driven shaft and the driving shaft both are given, see, motor shafts are 45 centimeter and 18 centimeter long, and their respective diameters are 9 centimeter and 4.5 centimeter. So lengths are given, diameters are given. What do you do with this data? Using the data of the diameter, you find the value of polar moment of inertia. G is already given, length is already given. So using the data of diameter and length and modulus of rigidity, you make use of this equation to find the values of KT for the driving shaft and driven shaft. So this is how you arrive at KT1 and KT2. And once you arrive at KT1 and KT2, what is the next step? The next step, obviously, as we have already detailed out, is to remove the gearing. Why are we so confident that we want to remove the gearing and do not want to keep them? Because the problem specifically states to neglect inertia of gears. Now there is another caution. See, I would deviate from the topic for a while. This is a matter of serious concern because even very intelligent and very careful students make mistakes here. The value of the modulus of rigidity is given in kilogram per centimeter square. It's a word of caution. All of you must convert the units to standard SI system first of all. I'm not going to dwell on how to convert kilogram per centimeter square into SI unit. What is the SI unit of kilogram? Kilogram here is not mass, it is actually kilogram force. Kilogram force has to be converted into Newton, centimeter has to be converted into meter. If you do not do this, your answer will be wrong. Even if your concept is right, your answer will be wrong. And depending on the examiner, you might lose a certain amount of marks for this. Maybe a lot of marks, because some examiners simply deduct marks by looking at the final answer. And if it does not match, they do not dwell or they do not wait to see कि भाई कहाँ mistake की है, silly mistake है, छोटी mistake है, बड़ी mistake है. Answer match नहीं हो रहा तो बस सीधे half number ही काट लो. So be cautious about the units. The units can be really tricky sometimes. So anyway, coming back to the topic, what do you do once you have the values of KT1, KT2, I1, I2? IG1 and IG2 are not required because we are ignoring the inertia of gears. Now what you have to do is, we have to follow the first conversion policy in which you ignore the inertia of the gears. So your system will eventually reduce to a system like this. What do we do? On the driving side, the inertia is maintained as it is. On the driving side, the shaft stiffness is maintained as it is. On the driven side, you replace the shaft with a new shaft having a new stiffness n square kt2. On the driven side, you replace the rotor with a new inertia n square I2. This is what you do. And now, what is the next step? The next step is to convert these shafts which are in series into an equivalent shaft. हर्षित, आवाज आ रही है मेरी?
हाँ सर.
ओके, अपना लेक्चर तो ऑलमोस्ट खत्म होने वाला है, बट आई एम रिकॉर्डिंग दिस सो यू विल गेट इट इवेंचुअली. ठीक है, इसमें थोड़े से न्यूमेरिकल कैसे ट्रीट करने हैं, पिछले वाले टॉपिक के उसी पे काम चल रहा है. So just stay with me for some, let us say 5 to 10 more minutes, and then we will be done with the lecture.
ठीक है सर.
Now the next step is to convert this stepped shaft into a singular shaft of uniform diameter. And how do we do that? First of all, let us reduce some complexity. Instead of writing n square kt2, let me just write it as kt2 dash. So this is n square kt2, and instead of n square I2, let me simply write it as I2 dash. So this will be n square kt2 is kt2 dash, and n square I2 is I2 dash. Now the shafts are in series, so I will simply get kt. Instead of writing kt equivalent and all, I will simply write it as kt. Kt can be obtained as by applying the formula for springs in series, because these shafts are basically acting as torsional springs in series. So it will be 1 upon kt1 plus 1 upon kt2 dash. Now since kt1 and kt2 dash, both the values are known, you get the value of kt. And once the value of kt is known, this entire system reduces down to an equivalent simple system. I1, the equivalent shaft stiffness kt as obtained from the above equation, and I2 dash, the equivalent inertia of the pulley. Now this becomes a 2 degree of freedom system, and we follow the procedure for solving a 2 degree of freedom system exactly as we have dealt with in the previous classes. So for this, I want you to go and refer कि भाई दो पुलीज या दो रोटर्स हैं I1 और I2 डैश, जिनकी वैल्यू पता है, बीच में एक शाफ्ट कनेक्टेड है, तो इसको दो नेचुरल फ्रीक्वेंसीज निकलेगी, कैसे निकालना है. आई विल very quickly I will guide you through the steps. अगर आपको रोटरी सिस्टम्स में कंफ्यूजन होता है, जैसा जनरली स्टूडेंट्स को होता ही है, तो फटाक से इसका एक M1 बीच में स्प्रिंग और M2, ये देखो क्या किया है. रोटरी सिस्टम में इनर्शिया को मास से रिप्लेस किया, टॉर्शनल स्टिफनेस को K से रिप्लेस किया, इनर्शिया को मास से रिप्लेस किया. ये रफ वर्क है, माइंड इट. डू नॉट डू दिस इन फेयर. ये सिर्फ उन लोगों के लिए है जो रोटरी सिस्टम से डायरेक्टली डील करने से डरते हैं, या जिनको थोड़ी सी प्रॉब्लम होती है रोटरी के अंदर, तो वो उसका एक इक्विवेलेंट लीनियर सिस्टम बना लें और उसके लिए फॉर्मूले लगा करके जो भी अपना तैयार करना है उसको तैयार कर लें और एज इट इज टेम्पलेट में प्लेस कर दें. क्या करने का है? हाउ डू यू मेक इट? फर्स्ट ऑफ ऑल यू मेक द मास मैट्रिक्स. क्या कर रहे हैं अपन? फ्रीक्वेंसीज और मोड शेप्स निकालने की बात कर रहे हैं. M1 0 0 M2, ठीक है। तो अगर मास मैट्रिक्स बन रही है, सिमिलरली यू कैन प्रिपेयर एन इनर्शिया मैट्रिक्स, ठीक है। इनर्शिया मैट्रिक्स को अपन जे मैट्रिक्स लिख देते हैं, क्योंकि आई मैट्रिक्स का मतलब आइडेंटिटी मैट्रिक्स होता है। हालांकि अपन नोटेशन के हिसाब से देखें तो इनर्शिया की मैट्रिक्स बनानी चाहिए, लेकिन अगर आई मैट्रिक्स लिखूंगा तो एग्जामिनर आपका एक्सपेक्ट करेगा कि आप यहाँ पर आइडेंटिटी मैट्रिक्स बनाना जा रहे हो, तो इसीलिए आई की जगह जे यूज कर लेते हैं अपन। सो जे मैट्रिक्स वुड बी वेरी सिमिलर। M1 M2 की जगह क्या लिखोगे, I1 और I2 डैश लिख दोगे, दैट्स इट। So here you will get I1 0 0 I2 dash. Next step is to prepare the stiffness matrix. Stiffness matrix बनाने के लिए आपको मैंने बहुत डिटेल में इन्फ्लुएंस कोएफिशिएंट्स वाले लेक्चर में सारी चीजें बताई थी। आई एम नॉट गोइंग टू रिपीट इट बिकॉज आई एम सिंपली गिविंग यू द हिंट हियर। आप देखिए स्टिफनेस मैट्रिक्स कैसे मैं हवा से निकाल के लाता हूं, वेरी क्विकली। शॉर्टकट ट्रिक्स आपको सब बता रखी है, कॉन्सेप्चुअली जाएंगे तो काफी टाइम लगेगा। एक स्प्रिंग दो मासेस के बीच में कनेक्टेड है, फर्स्ट मास पे कौन कौन से स्प्रिंग कनेक्टेड है, ओनली के। सेकेंड मास पे कौन सा स्प्रिंग कनेक्टेड है, ओनली के। फर्स्ट और सेकंड के बीच में कौन सा स्प्रिंग कनेक्टेड है, ओनली के। पुट अ माइनस साइन एंड के। ये देखो फटाक से मेरी के मैट्रिक्स बन गई। तो अगर के मैट्रिक्स ये है, तो मेरा जो एक्चुअल रोटरी सिस्टम है जिसमें मेरे को टॉर्शनल स्टिफनेस की मैट्रिक्स चाहिए, व्हाट डू आई डू, बिल्कुल डिट्टो इसी का हूबहू स्टिफनेस मैट्रिक्स तैयार कर दो। अब देखो ये जो पार्ट अपन कर रहे हैं, दिस पार्ट is not a part of the detailing of geared systems. Geared systems का explanation तो यही खत्म हो गया जब मैंने आपको ये बता दिया कि ये आपका इक्विवेलेंट सिस्टम बन गया है। अब इसको 2 डिग्री वाले तरीके से सॉल्व कर लेना खुद ही। We have already finished this numerical problem. I am just revising what we have already learned. अब तो ये 2 डिग्री को सॉल्व करने का तरीका है। Okay, what do you do once you obtain your mass matrix and stiffness matrix? The next step is to construct the dynamic matrix. Dynamic matrix कैसे निकालते हैं, mass matrix का inverse multiplied by the k matrix. This is called as a dynamic matrix. तो obviously dynamic matrix आपके rotary system के लिए कैसे बनेगी, it will be the inverse of your J matrix multiplied by the KT matrix. अपन को तो चाहिए ये आप लोग रफ में चला रहे हो, ठीक है। एक दो बार देख लोगे तो फिर आपको ये काम रफ में करने की भी जरूरत नहीं पड़ेगी। यू वुड बी कॉन्फिडेंट इनफ टू डायरेक्टली डील विद रोटरी सिस्टम्स, बट ऑब्वियसली प्रोवाइडेड दैट यू डू इनफ नंबर ऑफ न्यूमेरिकल प्रॉब्लम्स। आपको ट्यूटोरियल शीट्स में बहुत सारे न्यूमेरिकल प्रॉब्लम दे रखे हैं, सॉल्यूशन भी साथ में दे रखे हैं। अब ये टाइम आपको निकालना है कि आप वो प्रॉब्लम अपने हाथ से करके देखते हो कि नहीं देखते हो। अदरवाइज फिर एग्जाम में टाइम लगेगा, फंबलिंग होगी, प्रॉब्लम्स विल बी देयर। एनीवे, once again we have a very easy trick to get the inverse of a diagonal matrix. Diagonal matrix क्या होता है, diagonal matrices are those matrices in which the numerical entries exist only for the diagonal elements. All the elements apart from the diagonal elements are zero. So as you can see, your J matrix and M matrix both are diagonal matrices. और कहीं पर भी डायगोनल मैट्रिक्स मिल जाए और उस डायगोनल मैट्रिक्स के इनवर्स को निकालने की बात की जाए तो बोलना साहब मजा आ गया। क्यों, क्योंकि आपको इनवर्स निकालने के लिए जो एडजॉइंट, कोफैक्टर, डिटर्मिनेंट, वो सारे काम करने होते हैं। कुछ नहीं करना, सिर्फ एंट्रीज को अपनी अपनी जगह पे इन्वर्ट करके छोड़ दो, एज सिंपल एज दैट। तो आपकी मास मैट्रिक्स, अब अपन इसका सहारा ना लें, सीधे जे मैट्रिक्स का इनवर्स अगर मैं निकालना चाहूं तो क्या होगा, जे मैट्रिक्स इज दिस। तो जे मैट्रिक्स का इनवर्स जो है सीधे सीधे लिखूंगा मैं, दिस इज 1/I1 0 0 1/I2 डैश, खत्म बात, इनवर्स हो गया। Now I have to multiply it with the KT matrix, which is KT minus KT and KT. इन दोनों को मल्टीप्लाई करेंगे तो क्या आएगा? The D matrix will eventually look like this. Multiplication, I hope you know already how to do it. This will be KT upon I1. Here it will be minus KT upon I1. Here it will be minus KT upon I2 dash. Here it will be KT upon I2 dash. ये आपकी डायनामिक मैट्रिक्स बनेगी। डायनामिक मैट्रिक्स बनाने के बाद का क्या स्टेप होता है? ये सारे स्टेप्स मैंने आपको जब कराए थे तो बोले थे कि रटने हैं आपको, क्योंकि न्यूमेरिकल प्रॉब्लम करते टाइम यू डोंट हैव द टाइम टू थिंक अबाउट द थ्योरी बिहाइंड ऑल ऑफ दिस। थ्योरी करने लग जाओगे तो बहुत लंबी चौड़ी जाती है, तो इसीलिए थ्योरी को समझ लो पहले, जैसा अपन ने क्लास में कर लिया है, और अब उसके बाद जो न्यूमेरिकल को सॉल्व करने के स्टेप्स हैं वो आपके टिप्स पे होने चाहिए, या बिल्कुल सीधी सीधी भाषा में बोलो तो रटा हुआ होना चाहिए, तभी स्पीड बनेगी न्यूमेरिकल की। तो एनीवे, द नेक्स्ट स्टेप आफ्टर दिस इज टू अप्लाई दिस इक्वेशन कि डी मैट्रिक्स में से लैम्डा टाइम्स आइडेंटिटी मैट्रिक्स डिडक्ट करके ओवरऑल सॉल्यूशन का डिटर्मिनेंट लें एंड पुट इट इक्वल टू 0। ये स्टेप क्या चीज है? इफ यू आर फेयरली well versed in matrix algebra, then you know कि ये जो स्टेप आपको रटने को कहा जा रहा है ये बेसिकली ईगन वैल्यूज निकालने का और ईगन वेक्टर्स निकालने का रास्ता है। तो डायनामिक मैट्रिक्स निकाल के डायनामिक मैट्रिक्स की जो ईगन वैल्यूज हैं वो ऑटोमेटिकली आपके सिस्टम की फ्रीक्वेंसीज का स्क्वायर होती है। ये है इसका राज। So basically this lambda parameter that you are introducing here, actually it's nothing but the square of the frequency that you desire. जो चीज आप निकालना चाहते हैं वो उसका स्क्वायर ही है ये लैम्डा। So for now you treat it like lambda. अब आइडेंटिटी मैट्रिक्स जब मैं डी मैट्रिक्स के साथ एसोसिएट करूंगा तो इस आइडेंटिटी मैट्रिक्स का साइज भी वही होगा जो डी मैट्रिक्स का होगा। डी मैट्रिक्स का साइज क्या है? It's a 2x2 matrix. So what would be the size of the identity matrix that I'm going to use in my equation? It will be also 2x2. अब इस इक्वेशन को जल्दी से अप्लाई करें। लैम्डा टाइम्स आई क्या बन जाएगा? लैम्डा 0 0 लैम्डा। ये डी मैट्रिक्स में से मेरे को ये माइनस करना है पहले तो, ठीक है? तो शॉर्टकट में दिखा देता हूं क्या रिजल्ट आएगा। आप लोग वैसे करके देखोगे, लिख के देखो, क्योंकि आपकी प्रैक्टिस नहीं है ना इसीलिए टाइम लगेगा आपको। अदरवाइज आई कैन सिंपली लुक एट इट एंड से कि क्या आएगा ये। दिस विल बी के टी अपॉन I1 माइनस लैम्डा माइनस के टी अपॉन I1 माइनस के टी अपॉन I2 डैश and this will be kt upon I2 dash minus lambda। इसका डिटर्मिनेंट निकालना है और इक्वल टू 0 करना है मुझे। नाउ इफ यू जस्ट हैव अ लुक एट दिस स्ट्रक्चर, इसका डिटर्मिनेंट निकलने का मतलब है दिस मल्टीप्लाइड बाय दिस माइनस दिस मल्टीप्लाइड बाय दिस। सो ऑब्वियसली यू कैन सी that you are going to get hold of a quadratic equation in lambda। क्वाड्रेटिक इक्वेशन को सॉल्व करोगे तो आपको लैम्डा 1 लैम्डा 2 दो वैल्यूज मिलेगी। ये बेसिकली आपकी ओमेगा n1 का स्क्वायर है और ये आपकी ओमेगा n2 का स्क्वायर है। और एक और चीज मैं 100% शर्तिया रूप से कह सकता हूं, अगर इस सिस्टम को सॉल्व करने को नहीं कहे और सिर्फ आपको दिखाएं और ये पूछे कि बताओ इस सिस्टम की खासियत क्या है, what is special about this system, because there is something special about this system। ये एक नॉर्मल सिस्टम नहीं है। तो आपका जवाब फटाक से होना चाहिए This is a degenerate system. Semi-definite system. What is a degenerate system or a semi-definite system? What is special about such a system? The speciality is that the first natural frequency is always zero. या फिर और थोड़ी सी सरल भाषा में, आम आदमी की भाषा में कहें तो ये होगा, हालांकि ये 2 डिग्री ऑफ फ्रीडम सिस्टम है जिसकी 2 फ्रीक्वेंसी आनी चाहिए, लेकिन इसकी एक ही फ्रीक्वेंसी आएगी क्योंकि पहली फ्रीक्वेंसी शर्तिया रूप से 0 है इसकी. दिस इज अ प्रॉब्लम विद द सेमी डेफिनेट सिस्टम्स. तो सेमी डेफिनेट इसलिए इसको कहते हैं क्योंकि 2 डिग्री का होने के बावजूद इसकी एक ही फ्रीक्वेंसी होती है. एक ही फ्रीक्वेंसी का मतलब कि भाई अब तो पक्का हो गया, ओमेगा n1 जो है वो 0 ही आएगा. करके देख लो आप इसको सॉल्व. यहां तक तो कर ही दिया है मैंने, इसके आगे आप सॉल्व करो, इस डिटर्मिनेंट को इक्वल टू 0 करो, इसके रूट्स निकालो आप. यू विल सी दैट द फर्स्ट रूट λ1 इज 0. 100% 0 आएगा. Only one frequency will be obtained, omega n2. So this is how you solve it. ठीक है. अगर इसी सेम प्रॉब्लम में, फॉर दिस सेम प्रॉब्लम, यहां पर लास्ट में इन्होंने एक छोटा सा क्लॉज डाला था, निग्लेक्ट इनर्शिया ऑफ गियर्स. इंस्टेड ऑफ दिस, इफ दे हैड गिवन कंसिडर द इनर्शिया ऑफ गियर्स, और ड्राइविंग गियर की इनर्शिया अलग से देते और ड्रिवन गियर की इनर्शिया अलग से देते, तो क्या करते आप? Then no problem. Instead of your equivalent system being reduced to something like this, it would have reduced to a system something like this. So this is a 3 degree of freedom system, but once again there is something special about it. What is special? Not so much special, because now we already know it is a degenerate system once again. तो इसकी कितनी नेचुरल फ्रीक्वेंसीज आएंगी? इसकी 3 नेचुरल फ्रीक्वेंसीज हम एक्सपेक्ट कर रहे हैं, लेकिन आएगी 2, क्योंकि पहली वाली 0 आएगी. सो वंस अगेन द प्रोसीजर रिमेन्स एब्सोल्युटली द सेम. आप जे मैट्रिक्स बनाएंगे, फिर के टी मैट्रिक्स बनाएंगे, फिर जे इनवर्स इनटू के टी मैट्रिक्स करेंगे टू कंस्ट्रक्ट द डायनामिक मैट्रिक्स, और डायनामिक मैट्रिक्स में से लैम्डा इनटू आइडेंटिटी मैट्रिक्स को माइनस करके डिटरमिनेंट को 0 करेंगे. सेम प्रोसीजर. अब की बार 2x2 की मैट्रिसेस की बजाय आपके पास 3x3 मैट्रिसेस आएगी, और 2 नेचुरल फ्रीक्वेंसीज की बजाय 3 नेचुरल फ्रीक्वेंसीज आप निकाल रहे होंगे. सो द प्रॉब्लम गोज लाइक दिस. अगर इनर्शिया ऑफ गियर्स आ गई तो 3 डिग्री ऑफ फ्रीडम सिस्टम बनेगा. इनर्शिया ऑफ गियर्स को अगर इग्नोर कर दिया तो 2 डिग्री ऑफ फ्रीडम सिस्टम बनेगा. लेकिन कैसा भी सिस्टम बन जाए, आपको दोनों सिस्टम्स को कन्वर्ट करना और उसकी फ्रीक्वेंसीज निकालना ऑलरेडी आता है, क्योंकि मल्टी डिग्री में 3 डिग्री का कर लिया है अपन ने, और 2 डिग्री में 2 डिग्री की प्रैक्टिस अपनी ऑलरेडी हो चुकी है. सो दिस इज एवरीथिंग दैट यू नीड टू नो एज फार एज योर सिलेबस गोज फॉर वाइब्रेशंस ऑफ गियर्ड सिस्टम्स. हालांकि ये आरटीओ एग्जाम में आज तक नहीं पूछा गया, बट यू नेवर नो. किसी दिन कोई टीचर बना देगा, ऐसा कोई न्यूमेरिकल उठा करके दे देगा, तो कहीं ऐसा नहीं हो जाए कि आपके पैरों तले जमीन खिसक जाए. सो इफ यू फाइंड टाइम, लिसन टू दिस लेक्चर इन डिटेल. 1 घंटे का लेक्चर है, इससे पहले वाला भी था. 2 lectures you have to spend some time. Otherwise it's your choice. You can say कि भाई आज तक कभी आरटीओ में पूछा नहीं गया है तो फिर क्यों पढ़ें, शायद अब भी नहीं पूछा जाए. It's your luck and it's your choice. ठीक है, we will stop the lecture here. हर्षित, आप एक बार टाइम निकाल के अगर आपका मूड हो तो देख लेना. हालांकि आपका पूरा वाइब्रेशन का डेटाबेस तो तैयार है ही, and anytime you have a doubt you can ask me. ठीक है?
यस सर.
ओके.
सर मैं एक चीज पूछा था सर, जैसे एक